Hello everybody! In this problem, we're going to find an nth degree polynomial function with real coefficients satisfying the following conditions. N equals 3, negative 5, and 4 plus 3i are zeros, as well as f of 2 equals 91. Notice how this particular problem is asking you to actually build a polynomial function. If you think about the way we build usually everything, for example, you're going to go to the store and you're going to buy a box of puzzle pieces. And you're going to put the puzzle pieces together to create some beautiful scenery. Well, usually on the top of the box, you have the end result, what that particular scenery should look like. And you're trying to fit the puzzle pieces together so that you indeed can achieve that beautiful masterpiece. That's exactly what we're going to do here. We're going to try to find a way for us to put all of these puzzle pieces together to create an nth degree polynomial function. And one of the theorems that you learned in the class was something that's called Linear Factorization Theorem. And I'm going to shorthand it by writing LFT. Linear Factorization Theorem is a theorem that will allow us to build a polynomial function. The theorem looks like this. F of x equals a sub n, and we'll talk about all the different parts in just a minute, a sub n times x minus c1 times x minus c2 times x minus c3 times so forth and so on. So we might have many of these linear factors. Notice how I've mentioned so many of these linear factors. Hence, the theorem is called Linear Factorization Theorem. This allows us to write a polynomial function in a factored form. So let's talk about all of these little pieces. A sub n. A sub n is what we called linear or leading coefficient. Remember, the leading coefficient is one of the most important portions of a polynomial function because we utilize linear coefficient when we look at the end behavior of the graph. So finding this real number is very important. Now let's also look to see what are these C's. Notice how we have many of them. We have a C1, C2, C3, and many more here. We call them CIs. The CIs are your zeros. And you've probably already heard me reading the word zeros. Look at this. Look at this portion of the problem, are zeros. So now you're probably seeing we're going to have to do something with the C's and something with the zeros. And that's exactly what we're going to do. Now, let's see how we can utilize all of the different conditions, all of the different givens, and see how we can also use the linear factorization theorem to put the two pieces together, to put all the pieces together. All right, let's read the problem. I'm going to start by reading n equals 3. It's this portion of the problem right here. Let me tell you what n equals 3 will give us. N equals 3. We know many things from simply reading what n is. Now notice, it leads to problem. Find an nth degree polynomial function. Look at this n. You see this n right here? So in this problem, we're finding a third degree polynomial function. That means the highest power of your polynomial function will be a 3. You will be creating a cubic function. Not only n equals 3 tells us that we're looking for a third degree polynomial function, it will also tell you how many of these C's you need. It also tells you how many of these sets of parentheses, how many factors you will create. So let's write a few things down. From n equals 3, we know we have 3 zeros. Okay, these are your C's. Those are your CIs, right? Those are your CIs. Look at this. All right. It also tells us that we will have 3 factors. And remember, all of these factors are linear. Okay, remember putting puzzle pieces together? Now let's see how we can utilize the idea of what n is to put the puzzle pieces together, because it will allow us to truncate all of these many factors because we only need 3 factors. Here's our polynomial function. F of x equals leading coefficient times x minus c1, x minus c2, x minus c3. And we don't have to write any further because we know we'll have 3 zeros and we will have 3 factors. Okay, now remember there are multiplications. Notice how I'm saying factors, right? All right, now let's see what else we can do. We now know the skeleton. This is the skeleton of our function, but now we have to put some, we have the bones, right? We have to put some muscles into it. So let's see what are the muscles. Well, notice how C1, C2, and C3 are the zeros. Look at this portion of the problem. So now we're on the next set of conditions. The next set of conditions says -5 and 4 plus 3i are zeros. Well, remember, your CI's are zeros. So now we can substitute. We can treat C1 as -5. We will substitute this imaginary number 4 plus 3i into the second root. And then we will need to find a way to get the third root, which I'll mention in just a bit. So now let's look and see how we can put some muscles into this function. Leading coefficient a sub n times x minus c1. c1 is -5. Okay, now a few things to keep in mind. Notice how my 0 was a negative, and I have a negative in my problem. Notice how I put my c in parentheses. X minus c2. c2, look at this particular 0, 4 plus 3i. Let's put that in parentheses. Okay, and then we'll have times x minus c3. Well, what is it going to go into the c3? Let's think about what this number really is. Notice how this number is written in the form a plus bi. Does that remind you of these imaginary numbers, complex numbers written in imaginary form? Let's talk about our complex numbers. Okay, a complex number written in the form a plus bi. All right, remember, complex numbers, they have conjugates, complex conjugates, right? Complex numbers come in pairs. So if we have a 0 written in the form a plus bi, we will have another one in the form a minus bi. If we start with the form a minus bi, then the complex conjugate will be a plus bi. These we call complex conjugates. Complex conjugates. All right, now let's see how we can create a complex conjugate. Our 0 is written in the form a, that's a 4, plus 3i, that's your bi. That means our c3 will be 4 minus 3i, where we change the sign of the imaginary part of the number. Now we can take this third c and substitute right in here. So now we'll have x minus the third 0, 4 minus 3i. All right? Look very carefully. Doesn't this look like a polynomial function in factored form? So by simply using linear factorization theorem, we were able to write a polynomial function in a factored form. Our goal, however, is to be able to simplify, to open all of our parentheses up. We have 1, 2, 3, 4, 5, 6 sets of parentheses. We're going to try to find a way to remove all of them. And that would be actually our step number 2. So let me go back. And one thing that I didn't write, and I usually write, is that this is your step number 1, where you're building this polynomial function. And in step number 2, which will be our next step, is where we simplify what we build. Okay? Now we're going to go from the innermost parentheses outside. So we will remove this set, and this set first. Let's look at our function. F of x equals, keep your leading coefficient. It's a very important number. Then we have x. Now this is a -1 multiplying by -5. That gives us a +5. All right, now let's simplify here. -1, we have 2 terms, distribute to all the terms. So now we have x, negative times positive. Oops, that will be a negative, not a positive. -4, and then negative times a positive, negative. Okay, now we'll do the same thing with the next factor. Remember, we have a -1. Let's distribute. Let's see what it's going to look like. X, negative times positive. and then negative times negative. Okay, remember we counted? We have three less set of parentheses. These are gone. This set is gone, and now this one. Now we only have 3 sets to deal with. All right, I'm going to give something as a hint, and I'm going to write this in a bracket, just like this. I always suggest this to my students. When you multiply at this stage, specifically at this stage, when you start multiplying your factors together, multiply the factors that have imaginary zeros first. Because it's going to allow you, at the same time as you're simplifying your parentheses, it's going to allow you to simplify your terms. So at the end, you have less terms to work with, hence less problems to make, right? So let's make sure to remember, multiply if you have, now if you have imaginary zeros, multiply your factors with imaginary zeros first. So that's what I'm going to do. I'm going to keep my f of x the way it is. I'm going to keep my leading coefficient the way it is. I'm going to keep my x plus 5 factor the way it is. But now I'm going to simplify. Okay, and this is going to be a little bit long, so make sure to keep track of what I'm doing. I'm going to take each term in this set of parentheses, and I'm going to multiply by each term in this set. Okay, so hence, I'll take x, and I will multiply by x. That's going to give me x squared. Then I'll take x, and I will multiply by negative 4. That's negative 4x. Then I will take x, and I will multiply by the third term in the second set of parentheses. X times positive 3i. Positive 3ix. Okay? Now, I'm going to take the second term inside the parentheses, and I'll do exactly the same thing. I'm going to multiply negative 4 by x. It's going to give me negative 4x. Then I'll multiply negative 4 by negative 4. That's going to give me a positive 16. Then I'll multiply negative 4 by a positive 3i. That's going to give me negative 12i. Okay, so these 3, the orange, these came out from the x. These 3 terms came out of the negative 4 being distributed, and now I'll distribute negative 3i. So I'll do the same thing. Negative 3i times x, it's going to give me negative 3ix. And then negative 3i times negative 4, a positive 12i. And then negative 3i times 3i, be very careful. Negative 3 times 3 is negative 9. Now, when you multiply your i's at the very beginning, multiply them exactly the same way as you multiply your variables. So if x times x gives me x squared, then I times I will give me I squared. And I'll tell you what to do with I squares in just a bit. But for now, make sure that you realize that this x was distributed to all the 3 terms. So was the negative 4 and a negative 3i. Okay? The next thing is another hint to all of you is to notice at this point in time, this is why it was important for us to multiply factors with imaginary roots first, because at this stage, and only at this stage, so pay attention, all the terms that have I will eventually go away. Okay, and I'll tell you why. They will actually sum up to 0. Look, positive 3ix, you see? Now you have a negative 3ix. Let me underline. A positive 3ix and a negative 3ix. If I combine them, I'll get a 0. You see? So those terms are no longer there. If you didn't multiply these out, you would have still had these terms. Now, let's look at the negative 12i and a positive 12i. If you combine them, they sum up to 0. Now, remember I said all terms with I. We have one more term with I. Well, there aren't any more I squared terms, you see, but can we do something with I? Let's remember something. And I'm going to write a little reminder right here. Since you already have the notes on conjugates, I can erase this area of the board. And let's talk about the imaginary, this I. All right, we know that I equals to square root of negative 1. Well, remember that I squared is negative 1. I cubed, if you don't remember how to figure this out, remember I cubed is I squared times I, and I squared is negative 1. Substitute negative 1 times I will get you negative I. So I cubed is negative I to the 4th can be written as I squared times another I squared. Each I squared is negative 1. Negative 1 times negative 1 is 1. And remember, they repeat in groups of 4. Now let's see. We have I squared. I squared is negative 1. Between negative 9 and I squared was a multiplication sign. So you're really taking a negative 9 and you're multiplying by negative 1. That's going to give you a positive 9. A positive 9 will eventually be combined with a positive 16. And if you look very carefully, the only terms that you have left are the ones that have no I. Terms with I went away. They either added up to 0 or they were simplified further. Now let's see what our function would look like. F of x equals your leading coefficient. Then you have x plus 5. Now let's simplify. X squared. We don't have any more quadratic terms, so I just brought it down. But when I move to the negative 4x, I have another term. They're very alike. Negative 4x and a negative 4x, I can combine them. That will give me negative 8x. This term is gone, so then I combine these two. So the next one that I have is a constant, a positive 16. And remember, it's going to be combined with a positive 9. Remember, negative 9 times negative 1, this product gave you a 9. So 16 plus 9 is a positive 25. Okay? Now look what we did. We went from 1, 2, 3, 4, 5, 6 sets of parentheses now to only 2. But we're going to have to go further because you can distribute, you can simplify this problem a tiny bit more. I need a little bit more room, so if you don't mind, I'm going to erase my linear factorization theorem. Let me recopy this up here. F of x equals my leading coefficient times x plus 5. And then I'm going to multiply it by x squared minus 8x plus 25. All right. So now, just like we distributed here, I'm going to distribute right here to open more of my parentheses. Let's see. F of x equals my leading coefficient. Now, as I distribute x, let's see what happens. X times x squared is x cubed. Now I'll distribute x by multiplying by negative 8 x squared. And then x times 25 will be positive 25x. And then I'll do the same thing with positive 5. 5 times x squared, 5x squared. 5 times negative 8x, negative 40x. And then 5 times 25 is a positive 125. Okay? Now, if you look very carefully, well, first thing to realize is, you might say, well, Dr. Kelman, you can go further. You can combine these two terms. You can combine these two terms, which is great. But before I combine, I want to point out something. As you go through this problem, you might forget what you were really doing. Okay? Now, read the problem very carefully. Again, find an nth degree polynomial function. Well, the n was a 3. Do you remember? That means the highest power was a 3. Look. If you look at all of the exponents, all of the powers on x, and this is a constant, the highest power is a 3. So you're indeed, this is the checkpoint, right? This is a checkpoint step. You're indeed creating a third degree polynomial function. But can you combine like terms? Sure. Now let's combine. So now let's see. F of x, and let me use a different marker since this step number 1 will blend. So I'll go back to my orange marker. So f of x equals a sub n, and then I don't have any more cubics, so I'll keep the x cubed But I'm going to combine negative 8x squared and a positive 5x squared. That's going to give me negative 3x squared. I can also combine positive 25x and a negative 40x. That's going to give me negative 15x. And then I have a positive 125. Okay? All right. Now, are we still, if we look very carefully, do we still have a cubic function? Yes, we do. So far, we're good. So far, we're good. The only piece that we don't know is we don't know this leading coefficient. And we know how important it is for us as we're looking at polynomial functions. So is there a way for us to find the leading coefficient? Yes. And that's going to be our next step. That's going to be our step number 3, to find that leading coefficient. If you go back to the problem and all of your conditions, we used this condition. We used condition on zeros. The only other condition we haven't used is this condition right here. Okay, f of 2 equals 91. This tells me that my function value will be 91. My output, my y coordinate of the point will be 91 if my x is 2, if my input is 2. Well, if the input is 2, that means I can input or substitute or plug in 2 for each and every one of these x's. So that will be my next step, is to find my leading coefficient. And like I've mentioned, I'm going to have to erase a little bit more. So I hope you have all this down already, as I need a bit more room so we can find that very important coefficient, right? And one more step, maybe this particular line. I think it will be enough for us to find that leading coefficient. All right. Let's see how we can find this leading coefficient. Again, remember, I'm going to use this idea, f of 2 equals 91, this idea to find my leading coefficient. A sub n. Okay, so how do we find a sub n? Step number 3. A sub n, that's what we need to find. All right, we know that the function value will be 91, so f of 2 will equal to 91 if all of these x's are 2, right? Well, let's see. F of 2 equals leading coefficient times x cubed, my x is 2, 2 cubed minus 3, x is 2, 2 squared, minus 15 times x, x is 2, times 2 plus 125. All right, look what you have. You have a sub n times some number, and we can find this number by simplifying, equals to 91. So again, let me rewrite it. Leading coefficient a sub n times, if you were to simplify all of this, you will get 91 equals 91. So you're saying some number times 91 equals to 91. Well, to isolate this number, divide both sides by 91. 91 divided by 91 is 1, and you know that the leading coefficient is 1. 91 divided by 91 is 1. That means if I go back to this simplified version of the polynomial function, this leading coefficient is 1. Once I plug in and substitute this leading coefficient of 1, I can then write what is and find what is my nth degree polynomial function. And that would be step number 4, to finally write it. After all of this that we've done, we want to know, what does it really look like? We found what it could look like without the leading coefficient, but now we found the leading coefficient. Let's look at our last step that allows us to simplify all the way and find our leading coefficient, to find our polynomial function. Step number 4. F of x. I'm going back to step number 2, right? Step 3 was simply finding the leading coefficient. But this is where we have our function. A sub n, it was a 1, times x cubed minus 3x squared minus 15x plus 125. And once you distribute this 1, now that leading coefficient doesn't have to be a 1. It's whatever the leading coefficient is, that's what you're going to substitute for this a sub n. Now f of x equals 1x cubed minus 3x squared minus 15x, because you're simply multiplying by 1, plus 125. And if you look very carefully, you have built an nth degree polynomial function with real coefficients. 1, -3, -15, those are real coefficients. You have a real constant satisfying the given conditions. N is 3, highest power is 3, it's a cubic. We used all of these zeros to build the function, and we utilized the idea of this point. This is a point on the graph. X is 2 and y coordinate is 91. We used this particular condition to find our leading coefficient. So we are done with the problem. Let me write this 3 a little bit more clear so you can see it. It's a third degree polynomial function, and we are done with the problem. Thank you.